welcome to my talk and welcome to the video. So I'd like to talk about Scalarverse, which is a framework for post-inflationary dynamics, which are mainly non-linear. And my name is Niki and I'm a master's student at the University of Göttingen. And beforehand, I'd like to thank Sean Hotchkiss for the possibility to talk or to give a talk on this cool conference. And I'd also like to thank my collaborators from the University of Göttingen, my supervisor for the master thesis, Jens Niemeyer, and the postdoc of ours, Frank, and of course also my colleague, Hyun-Kyu Lee, which is another master thesis student which works with me on the Scalarverse code. And from the side of Auckland, University of Auckland, I'd like to thank Richard Easter and Peter Heyman, so especially Peter because he is the other collaborator of the Scalarverse code, or better, the main maintainer of the code. So let's talk about where we are, or better, when we are. So the whole code kind of is embedded in the post-inflationary phase, which means we have inflation, and at the end of inflation, the code kind of starts, and after inflation, that's reheating. So the assumptions, or the main assumptions, are kind of that we have single feed slow roll inflation, which is like the simplest case, and further we assume that there's the inflaton potential which has a minimum, which has a quadratic minimum. This enables structure formation if the post-inflationary phase lasts multiple e-foldings, and of course, to make it last multiple e-foldings, we assume that the inflaton decays in a very small rate. Okay, so let's dive deeper into the post-inflationary phase, which is at the end of inflation. So we assume single-feeder slow roll inflation ends, and then there's a relativistic regime. So the inflaton behaves relativistically, and as most of you know, this is also called preheating and can be described by Klein-Gordon-Einstein equations, which is also sometimes named Klein-Gordon-Friedman equations. So this whole phase enables self-resonance. Basically, it even enables resonance itself, but since we are talking about single-feed slow-roll inflation, this is only self-resonant. And if this inflaton is there long enough or oscillates long enough, we will get into the non-relativistic regime, and this can be described by Schrödinger Poisson equations. That's first shown in Musoka 2000 and Musoka and al. 2019. Also, they didn't show Schrödinger Poisson, but they showed that it's possible to have inflation and then relativistic regime and then non-relativistic regime, and this non-relativistic regime described by Schrödinger Poisson. Yeah, this Schrödinger-Poisson part, or the non-relativistic regime, also supports structure formation, because if you have a potential with a quadratic minimum, the equation of state parameter would approximately, on average, would be 0. So it's literally like a meta-domination phase, and all this meta-domination phase even before reheating. I brought you the Schrödinger-Poisson equations just because I assume that most of you know the Klein-Gordon equations. Therefore, I thought maybe it's a good idea to show you Schrödinger-Poisson equations and how they merge. So the Schrödinger part is basically the non-relativistic approximation for the Klein-Gordon equation. And if you have the Einstein part of the Klein-Gordon-Einstein part, or the Friedman part, and take the non-relativistic limit, you get the Poisson equation. And the Schrödinger-Poisson equation are kind of a system of equations connected by the Newtonian potential. So you need the Newtonian potential for both. And of course, you have the field value psi now instead of phi, the approximation basically for the inflaton field. All right, so as you have structure formation, you could assume that for a simple case, the inflaton potential is quadratic even at the end of inflation, right? But this is a basic, simple case, or could be a basic, simple case. This would lead to no resonance. So the preheating phase literally had no resonance at that case. And if the inflaton evolves long enough, it gets into the non-relativistic phase and it would have structure formation. Eggemeyer et al. 2021 showed this, and they showed that solitary cores could form if they assume there's a purely quadratic potential, and these cores emerged at e-folding numbers 17 e-foldings. So it took 17 e-foldings from end of inflation to get some structures. Okay, so after we looked at the simple case where the potential is quadratic, Eggemeyer et al. 2023 started to look at more complicated potentials, for example, the axiom monodromy potential. And here the potential is in the large field proportional to phi to the power of 2 alpha, and in the small field it's approximately quadratic, so or in the minimum it's nearly quadratic, which means that after inflation ends there could be resonance in the relativistic regime, and in the non-relativistic regime afterwards there still would be structure formation. Especially I'd like to highlight here that these solitary cores formed nearly 10 e-foldings earlier than in a purely quadratic case, which means it's kind of interesting because if you have some constraints on the inflaton decay and the structure formate even earlier, it's kind of a good idea. I also brought you the power spectrum of the paper because here you can clearly see a resonance peak. So at some point in the resonance, the peak emerges, and the peak is still there in the non-relativistic regime. And as the power spectrum grows in the non-relativistic regime and perturbation grows, at some point the dimensionless power spectrum reaches 1, which we all know should be the point where structure formation gets nonlinear. Which is an interesting case because here we can clearly see that it's possible to create nonlinear structure formation in the phase after inflation, and that even before reheating, so kind of structure out of inflatons, and this could lead into gravitational waves, for example, or even primordial black holes, and that even before reheating. Benedict Eggemeyer, so Peter Heyman and Benedict Eggemeyer used 2 different codes for this. And the relativistic code was based on lattice easy and solved the Klein equation. And then they took the output and took it into the non-relativistic regime, which was Schrödinger Poisson solver. And the Schrödinger Poisson solver was axionics, which is motivated by fuzzy dark matter research. And they combined both pipelines, but with 2 separate codes. So the idea emerged of Scalarverse, which is in principle the whole pipeline they did in the paper, but all in one code. So we have the Klein solver, take the output directly, put it into Schrödinger Poisson solver, and therefore can have a unified framework for the inflaton dynamics, especially the nonlinear inflaton dynamics right after inflation and before reheating. So how does this work? The pipeline of Scalarverse, as I mentioned, is you have some initial field distributions from inflation, and you input those into the Klein solver. Then the Klein solver outputs the field values at certain times and certain grid points, even the scale factor evolution. And if you think about it, the scale factor evolution or the equation of state in the Klein regime is non-trivial because you don't have one certain equation of state because the inflaton oscillates. And with these field values, you could output or calculate these energy densities at certain grid points. And of course, you could also take the dimensionless power spectrum and examine this. But all this is kind of already done because it's literally preheating research. And what now next off is a good idea is taking all these outputs from the Klein-Gordon solver and input those into the Schrödinger Poisson solver, because this is kind of a great approximation to the relativistic regime, in the non-relativistic regime. A good approximation for the Klein-Gordon equations in the non-relativistic regime, and therefore they are kind of way more computationally efficient. So if most quanta in your simulation are non-relativistic, you could output the Klein-Gordon solver, input the values into the Schrödinger Poisson solver. Here, the Schrödinger solver solves the Schrödinger equation, gives the energy density, then the energy density is taken and calculates the Newtonian potential, and the Newtonian potential is calculating the Schrödinger equation again, or solving the Schrödinger equation again, in a literally iterative process, giving out the energy density at certain times, at certain grid points. And again, you can calculate the dimensionless power spectrum and see how structure emerges in the non-relativistic regime. What I really want to emphasize here is that Schrödinger Poisson is way more efficient from computational perspective than solving the Klein-Gordon equation itself, because you could do all this with Klein-Gordon Einstein solver, even the non-relativistic phase, but it would be literally kind of solving with a relativistic simulation, non-relativistic problem, which is, yeah, obviously computationally costly. Therefore, it's a really good idea to do this and see how structure emerges in the simulation. So what's the actual status of Scalarverse? Right now, the Klein-Gordon solver is already ready to run simulations, and the Schrödinger and Poisson solver are right now in development. So Q and I are working on the development of the Schrödinger and Poisson solver. It's literally part of the of our master thesis. And as some outlook, what could we do with kind of this simulation framework? We could examine the power spectrum, for example. So taking different input potentials, seeing how does changing certain parameters in the potential affects the power spectrum, and understanding the power spectrum even more. I could say the primordial power spectrum, because it's power spectrum even before reheating. And further in the future, one could examine gravitational waves with this code, because you have structure formation, especially nonlinear structure formation, so it would lead into gravitational waves, and one could examine or give some predictions for the gravitational waves. And yeah, maybe even more in the future, one could calculate the amount of primordial black holes with this whole simulation, which could result into heating up the universe even faster, even more in the reheating phase. So it's kind of a useful tool, having all this in one code and one pipeline, which self-consistently is solving the early universe dynamics. And in the end, I'd like to thank you for your attention, and hit me up with some questions about this whole presentation on the conference itself.